Hello everyone. Hi. Sorry about that. Just needed to get all my other groups online and engaged. So here we are. I think the streaming is working and we're ready. Today's stream is probably going to be shorter than the other ones that we've had before, and for a good thing. Maybe not even shorter. We'll see. But what we're going to be working on today is a little bit of an advancement on the work that we started yesterday. So yesterday, or on the last stream of this series, if you're watching later and it's in a playlist, we were working on the perceptron neuron, which is an artificial neuron that takes in binary. Let's go to that. That takes in binary inputs plus some weights and produces a binary output. I would say, a binary output. So I think this is in documents, and then this is going to be rudimentary and neurometric. Cool. So we had we made a sort of neuron input here, and then we had a fire perception formula, and then we also had a sum of weights formula. I mean function or whatever. So first of all, we're going to modify our fire perceptron formula, number one, and then we need to modify this so that it's a little bit simpler, so that we can kind of sort of make our intuition better. And then after that, we can go on to implementing the sigmoid neuron and see what makes that one different, and why is it different. I mean, this was all posited in my blog, or rather in my notes yesterday. The change from one to the other is going to be a one-liner. However, the thing is, in order to understand, it might even be more than a one-liner, because this function signature is going to also change. It might be more than a one-liner because that function signature is going to change. But the more important part is, why does it change? Okay, why does it change? So let's go back and look at our perceptron firing sequence, and then once we fix that and we kind of make it a little bit more intuitive, we can go and look at the sigmoid. Okay. So the change I want to introduce here is this one. If you sort of use I don't know what the name of the formula is, but if you move this threshold, so the formula for the perceptron is total of weights and inputs, total of weights times inputs, whether that total is above or below a certain threshold. So above or below. So this is less than or equal to. So this is above. Yeah, this is fine. Then we can basically do it. We can make a firing sequence based on that. However, if we rearrange this equation, so it's easier to read. Remember, we're going to put this equation is going to disappear deeper and deeper and deeper and deeper into our formula. And the reason it will do that is we're going to decorate it more and more with more detail. And so it's going to become a single part of our formula. So it sort of helps us right now to make this as simple as we can, to help our intuition, so that when we're looking at bigger, so later when we're looking at more complicated neural network formulas or neuron formulas, we are able to just identify where the core is and how it builds up from this. So this is why we're simplifying this. So let's look at a way of simplifying it. So there's this way. Let's simplify the way we describe perceptrons. There's this part here. I'll even zoom in so that we can see better. Let's simplify the way we describe perceptrons. The condition Total sum of weights times factors above threshold is a little cumbersome, and we can make two notational changes to make it simpler. The first change is to write the sum of the weights and the sum of the weights and the factors as a matrix multiplication. I think everyone knows that. So if you have let's say if you have two vectors, two column vectors. So let's make two column vectors of let's make them of the actual stuff in our, let's make them of the actual input. So we have a weight, we have a value 1 of cheese, and we have a weight 3, and then we have a value 0 of gluten, and we have a weight 5, and then these two can give us two vectors. So you can have it doesn't work, so let's write it somewhere here. We can have two vectors that look like this. I'll just write it so that it works, and then we can look at it later. So you can have two vectors. It's hard. I don't have latex on this machine, but basically you can have a vector of the weights, which of the values, which is 1, and then below that you can have a 0. That's the first vector. Okay, so this is the weights. This is the weights. This is the weights. Values themselves. And then over here we can come and have a vector of the weights. And then in this vector of the weights, we can have the first weight is 3, and the other weight is 5. So here, in this little group of numbers, we have two vectors, two column vectors. Yeah, if I remember correctly, we have two column vectors. And to get their totals, the easiest way we can do, if these are weights and these are x's, so let's put this is x and this is weights. The easiest way of getting a sum, an integral of this thing, which is an accumulated sum, is as a matrices you can do w times x. Okay, so that's a dot matrix, dot product, if you may. Okay, so that's what is being described here. So we can do it as a dot product of two matrices, and the dot product of the two matrices is equal to the integration of the weights and the values themselves. So basically an accumulated sum. And then if you follow plain mathematics, you can move the threshold to the other side of the equation. If you move the threshold to the other side of the equation, then you can have a different equation for 0 and a different equation for 1. You see, basically it's here. Okay, and based on this equation, we can now compute the thing that we were computing before. If anyone has any questions, please feel free to leave them on the chat, and I'll answer them. So let's go. Let's change this into the thing that we want. So if the weight sum, we can actually make it here. So let's see. Let's A out. Let's run that. So value 1, weight 3, value 0, weight 5. Sum of weights is 3, threshold is 4. There's no gluten. We can go. Let's see. Can we change this so that it actually returns the thing we want? Number 1, this needs to be a boolean. So this actually should be a boolean. This should be a bool, and then because a perceptron only does that, and then we're going to return weight sum minus threshold is equals to is no it's greater than or equal to 0. Is that what we want? Less than or equal to 0. Yeah. So if this is true, it will return a 1. If it's not true, it will return a 0. It will return a false. So first of all, let's just change this function, and then before we even change the signature of that, well, it's already that. We can go here and change the signature here. Bool makes it even better, makes it even more intuitive. And then in here we can go I bool fire. Okay, I think it needs me to do std bool. Include std bool bool.h. I think that's it. And then if it's if fire, cool. If fire, da. If not, dumb. Okay, cool. Let's see. Can we GCC this thing? GCC main. Okay. A out. If we have the same result, we can. Threshold is 4. There is gluten. We can't go. We got it wrong. There is no gluten. There is no gluten. There is no gluten. So where's the weight minus threshold? Weight sum. If weight sum minus threshold greater than or equal to 0, fire. No, this is greater than 0 should fire. Less than. Oh, okay. Less greater than has to be greater than. Greater than. But we still don't. Doesn't make sense that way. There's gluten. We can't go. That is not good. Still a little bit less than or equal to 0. That's fine. But that's fine. There's something. Our intuition is not exactly where it should be. Minus threshold. Weight sum minus threshold greater than 0. If it says fire, yes. There's no gluten, we can go. Wait, there's something I've kind of made opposite of. If weight sum is more, no, so this is all a distraction here. So let's remove all of this. Let's remove all of this and fix our logic from here. So I know that if I do this, I know the fix is this. Less than or equal to. C less than or equal to. Yeah, I just need to see the formula for that. Less than or equal to, less than or equal to, less than or equal to. No, I want that one, this one. Less than or equal to, so that's fine. So I know this is the answer. I know this is the answer. But I don't know why that is the answer. So let's see, GCC main, A out, there's no gluten, we can go. Less than or equal to 0. So let's go back and realize why that is the answer. Weight sum is less than or equal to 0. So less than or equal to 0. Okay, let's see here. If weight sum is less than or equal to 0, go 0. If weight sum is greater than or equal to 0, go 1. Okay, so first of all, let's change it and see that actually it does work. And then we can sort of logically go back and see that there's gluten, we can't go. So is this a thing of the caller? Is it that we need to change the color? No. If fire, there's gluten. There's no gluten, we can go. If else, there's fire perceptron. This is probably should be in a check gluten function somewhere, but let's see. So weight sum minus threshold is less than or equal to 0. You should return a 0. Is that what is happening? It should return a 0, so don't fire. Weight sum plus minus threshold, if that is greater than 0, you should return a 1. Yeah, we have a gluten recognition system. We do have a gluten recognition system because it fires if there's no gluten, if there is gluten, but it doesn't fire if there is no gluten. So if it fires, no, this is an opposite one because it fires when there's no gluten. It fires when there is no gluten. This is the perceptron we want, not the inverted perceptron that we had. Okay, cool. Let's hold on to that. So that becomes the formula. Now, there's another thing. There's another step. So there's another thing. There's another step that we were looking at. So there's something called a step function and a sigmoid function. Step function. There's a step function here, and the step function is basically a function that defines moving either from 0 to 1 or from 1 to 0. But the way it does it is it does it on a brick wall scale. There's a brick wall way it moves. There's no gradual move from 0 to 1, and there's no gradual move from 1 to 0. And this is a problem. Why is this a problem? Later, when we have the thing about deep learning is you want to use networks of neurons. You want to use networks of neurons, and that's why they're called neural nets. Okay, you want to use networks of neurons to be able to perceive or observe and then make logical conclusions about it. So basically what I'm saying is you want to use networks of neurons to learn. That's because that will be that's the way you do it when you're using neural networks. You show the computer some results, and then it makes the rules for those results to come up. Okay? The problem with the perceptrons that we have is that they go suddenly from 0 to 1 or from 1 to 0. They can flip very suddenly. At the border, they flip. And that becomes a problem when you have multiple layers of perceptrons, or rather, more than one layer of perceptrons. So when you're learning and you have many perceptrons arranged in something like this, this is actually the thing that describes the problem. When you have many perceptrons, let's find a less contrived. Here you have this many layers. If you have that many layers, if one of the layers is not that smooth, and a small change in input can make a large change in output, because the perceptron can go from 0 to 1. That's a large change in output. Okay, and then this will change the rest of the network in hard to predict. You don't know why it's changing like that. You know the one thing that has changed, but you don't know why every other thing is changing that way. And the reason is because the way the perceptron changes states. So what we want to do is we want to move towards a sigmoid function, neuron. And a sigmoid function is a function that moves between 0 and 1 in a very gradual way. That way, if you have a small change in the weights and the thresholds, okay, not the factors. We're considering the weights and the threshold. If you have a small change in the weights and the thresholds of the thing, then you should get a small change in the outputs. And that way you can gradually move towards the correct output. And that way you can also sort of automate this learning because you have that sigmoid curve. The importance of this curve isn't really it's not really the shape of it, or rather it's more the smoothness of it. The smoothness indicates that you can move very gradually in very small steps. Like you have if you know anything about signal processing, which you kind of would if you're looking at this, or you might it's adjacent curious to this. There's a concept called binning, and the larger the bins you have, the more of a gradual process you can go. So this is if you can divide the steps smaller, so you can go from there's a function that can go from 0 to 1, and then there's a function that goes 0, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.91, and then there's one that goes 0.001, 0.002, 0.003, 0.004, 00, like that, as so on and so on and so on and so forth. And that what you have is you have very little gradual steps, which are called real numbers, depending on, well, they're all real numbers, but depending, you can have small gradual steps that you can move towards the implementation of this. And that implies that we're going to change quite a bit of our application, I think. I'm going to leave this this as it is, and then let's add a few more. So this, first of all, this becomes a perceptron input, because it's made of perceptron data. Perceptron. Yeah. And this is also a perceptron input. Perceptron. Okay, and then this doesn't exist. This is also a perceptron input, and then this is also a perceptron input. Okay, and then let's keep going and see for a perceptron. This one takes a perceptron input. Perceptron. Okay, I think that should be it. And the sum of weights, sum of perceptron weights. And then this takes perceptron input. Oh, no, perceptron input. Okay, and then it's a sum of perceptron weights. We will make this efficient later. It's right now it's just to perceptron input width. Okay, cool. So now let's add a new thing in our thing. So let's make a struct. It's sigmoid input. Okay, and then now the thing about our new struct is that if we're going to get something that generates a sigmoid curve, what we need is not just we need for both the weight and the value to be real numbers. 1 and 0 are real numbers, but real numbers with floating point numbers. So I'll go here and I'll do something like float value, okay, and then float weight, okay, and then in here I'll go like that, And then what that now just gives us the perceptron, this, yeah, fire perceptron. Why? I know why. Cool. So you have that. We have that, and this is not neurons. This is perceptron. This is okay. If I do that and I do that and I get A out, I should get the same thing. Threshold is 4. Base gluten, we can't go. Okay, cool. So now let's go back and implement. This. So the first thing we need to do is define a sum of. Let's first of all make a bool fire sigmoid. This is not a bool fire sigmoid. This is a float fire sigmoid because it can come back. Remember the curve that we're trying to be. It can come back anywhere along the curve. It doesn't have to be. And then we can use something with 0.5 in there. And then struct. It takes in struct. Sigmoid inputs. Input. And then we can say that inputs. Inputs. And then we can have. Even here, the threshold can be a float, so that you can just move it to all float. And now you see why you can have an AI chip. You can have an AI chip. This is basically, you have something that can enable you to do floating point stuff, and that becomes an AI chip in some sort of weird ways. And then, some chips have neural nets and stuff. Let's put a threshold in there as a float. Threshold. I'll just threshold, and then in there we can just put an int length, input length. So let's define that, and then we can also have float sum of sigmoid weights, sigmoid sum. I don't know what to call that, but let's just a better name might come up later. If you have a name, you can feel free to suggest it, and that would be nice. Sigmoid input, and then this will be inputs, and then this will be input length. It's kind of a little obtuse to have both of them, but it's fine. So let's this is yep. So my code was right the first time. So cool. So let's bring this two functions over here. Let's bring it over here and just do some implementations of them. Let's do a couple of implementations. So let's start with the sum. I can actually just use the sum I have below. Let's use the sum we have below. So later, when we've created enough problems for ourselves, we realize that we can optimize this using something called SIMD, and that's going to make it very interesting, because at some point we can do probably both. I don't know if it's fire sigmoid and sum of weights together, but for sure we can do sum of weights as one as one operation. Single instruction, multiple data. Let's look at that quickly before we go on. So you have to create enough problems so that you can fix the things you want to fix in life. So SIMD is this. So SIMD, single instruction, multiple data. When we have a nicely working sort of mock of a neural network library, we can go and add, we can give performance, we can improve performance on these neural network libraries by implementing. We will have a lot of matrix operations where we're doing calculations with matrices and vectors. And when we have that, we can probably, you want one instruction applied to 512 items. You can go and do that something also. So basically, we're making a path to writing assembly. That's kind of where we're going. Making a path to writing assembly. So that is going to be that, and then for int that's going to be that. Input values I times input weight return sum. Yep, that's fine. And then fire sigmoid is going to be the same one. I just want it to be the same one, so that v but now this is going to be different. Fire sigmoid is going to be different. Fire sigmoid is going to be different. Why is it going to be different? Because we're going to fire based on some sort of threshold. That's fine. We will fire based on some sort of threshold. But the way we actually calculate the output is not going to be a 0 or a 1. It's going to be, we're just going to, rather than the thing, wait, I have a message somewhere. Rather than, is this okay? Cool. Is that okay? Cool. So yeah, rather than returning a boolean, we're going to return a floating point number, which is fine, which is going to be the result of the sum of weights, blah, 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 by that. So the way, instead, rather than do the sum of weights and the dot product of the weights and the values minus the bias, what we're going to do that is going to be 1 plus the exponential of the negative of that, the negative of the value that we're going to get. And this is so that, because if we have a large value, we want to squeeze all our outputs between 0 and 1. So we want 0.02 and 1.0 to be the valid things, and anything in between, real number wise. So that could be 0.01, 0.001, 0.01, 0.02, 0.03. Just go like that all the way until you get to 1. Okay? So because we still want a 0 or a 1, we're still in the digital realm, so we still want a 0 or a 1 reply. So let's compute. Let us compute this. It's quite simple. I already have it in my blog here. It's just, the computation is not the part that's difficult. It is the weight of the sum. This is wrong because it's weight sum negative weight sum minus weighted sum minus bias. So we should probably also modify that. Documents. We can actually just do it from here, and let's go documents, Gaia Ocho's post, and then we can even go 2025. I think yesterday was the 30th. And then we can do that one directly, and then we can say exp, and then we can just find that. And then this is going to be weighted negative of weighted sum minus bias. minus bias. Minus bias. And bias is just negative threshold. So we can say plus negative threshold. Or you can just say minus bias. Okay, cool. So that's gonna be that. So let's go implement that. So we will have a weighted sum. We'll have a weighted sum. Bool fire. Yeah. Let's yeah. B y. Let's do that. Let's do y. And then I wanted to put it in fire. We have a fire sigmoid function, yeah. Fire sigmoid. It's not going to be too much different, but it's going to be different enough that it's B. Yeah. Tab. And then I think here I need yeah, this is going to be the thing that we're going to make different, and then there's that. This is not going, we're not going to print, we're going to do value weight F. We want an F as well. Isn't that what the problem is? Sum of perceptron weights. This is sum of sigmoid waves. Sig. Okay, cool. And then here we don't have a threshold. Yes, we do have a threshold. Threshold is going to be. This can also be a float. This can also be a float because the weight sum should be a float. So sum of float sum. I see what the problem is. It is you here, so we should get a float. And then that should give us a float, but instead of returning this, instead of returning a Boolean value here, we're going to return, well, we can just make a float ret here. Float ret. We can actually go up here and do a float ret for, yeah, let's just make the float ret here. Float ret. Yeah, so that we can reuse this a few times instead of allocating stuff. And then it's going to be, anyways, that's what we're going to return. And then in here we're going to go and say I ret, and then we ret, and then somewhere down here we're going to return I ret, and then in here we're going to do something like ret is equals to 1 over 1 okay, 1 plus the exponential of the ret. This is going to be ret minus threshold. Okay, but we want the negative of this, and then one close that, and then close that properly, and then that. And then we want to return that, and we want to return that. And there's an issue. This probably wants me to X, that's std math. Wait. I can ask my thing what I need to do. Let's just ask the computer what we need to do so that we can fix it. Yeah. Okay. That's alphabetically before S, so include math. Okay. So this should sort of work. let's do fire perceptrons. Fire, let's do an input. Oh, it needs a different input anyways. So let's actually do that. This will be cleaned up. We're writing a library, so our main is always going to be dirty because we are simulating an implementation inside a library, but it's fine. Return ret equals to 0. Okay, yeah, that's fine. That's fine. SP, and then we can do cheese input. No, I don't want cheese input. Sigmoid cheese. Yep, fine. Sigmoid. Okay, let's do something like 1.0, 1.5, and then 3.2, and then we want to go sigmoid gluten. Okay, and then we want something like 1.0, and then this one's going to be 4.5. So it's still a bit heavier, And then here, what we want to do is we want this not to be perceptron inputs. We want this to be sigmoid. Yeah. And then here we want it to be sigmoid. Yeah, so that's that. We have the sigmoid inputs there, and then what we want to do is basically, struct sigmoid input s inputs. And then let's do that, and then we're gonna say equals to sigmoid cheese, and then we can do sigmoid gluten, sigmoid y. And then let's just compute something and call it out. So let's say float s result sres equals to fire sigmoid, and then in here we pass in an address to s inputs. It's already an address. No. S inputs. It's already an address, so we can just pass it in like that, and then we can say 4. What is 4? I think that's a threshold. Yeah, let's put it at 4.5. It's fine. Let's put it at that. And then say 2. And then let's do that. Fire sigmoid. And then what I want to do here is printf something. Let's just printf the result. Printf sigmoid fire result. Sigmoid fire result. Do we use the threshold? 4.5. Yeah. Let's put that in like I like to do when I'm doing an error, because that's sres. And then that's it. That's pretty cool. Yeah. Let's compile that. Do we think that's compiling and running? Let us see where that compiles and runs. So GC main fire sigmoid exp y. I know the issue. I need to GCC link math. That's the problem. Yeah. So I already saw the issue, the answer. So it's GCC-LM. No. I just want to. Yeah. No, I don't want to do that. I want to do it the easier way, the one-liner way. Why would I? Come on. Okay. It's just that, and then LM at the end. That's what I forgot. Ha! So that works. A out. There you go. Wow. So let's put a space there. Let's put a space there. Put a space in what we want. Let's put a space in what we want. There's somewhere we're missing a space. We're missing a space in the main function somewhere here. Okay, cool. So let's do that. Let's clear that, and then let's run the function. Cool. So the fast set, this set, that's running a perceptron. All the way to all the values that are being dealt with are binary values. Well, binary values and integer values, if that makes any sense. The presence of the value of the thing is a binary value. It's either 0 or 1. It's there or it's not. And then in the sigmoid function, what we can see here is there's oh wow, this is amazing. You see what is happening here? So the thing is, we can say here, here we can say this. Here we can say this. We do have a fire result at the bottom, so we can end up returning we can end up returning a boolean, and the boolean would go something like. So if we want to return a boolean, let's return a boolean from our fire sigmoid. Let's return a boolean from a fire sigmoid so that we can make it the complete library at once. Boo, and then here I would return. We would return ret over 0.5. And then I know what I need to do. I need to come up here, and this is, instead of returning a float, we need to return a bool so that we can do that. And then in here, I'm going to also change this so that we can get a different result. I'm sorry. And then I want to basically do this. Y. And now to come here and say, instead of actually this, I'll say this, and then I'll go like, yeah, SP. And then let's do that, and then we can do here if sres, so that we're just, our neuron also always fires. Let's make our neuron always fire so that we have a standard neuron API. It fires or it doesn't. Okay, We have a standard, so you can use this neuron from everywhere else, and we're not we're not leaking abstractions. How am I talking about leaking abstractions here in a one file thing? But so let's say that if sres. No, but this is also a bool. And then it's that. Actually, we can do bool. We can just reuse fire here. Fire equals to that. And then in here we can just come if fire. So I've made, note, I have made the both functions a little different. One of them has gluten, one of them does not have gluten. Let's see what happens when we do that now. Okay. So let's do GCC main LM. Okay, cool. And then A out. Let's see. Oh wow. I'm confused. I am confused. So just a moment. There's number one, there's going to be there's no gluten, we can't go. So there's supposed to be it's supposed to be a new line somewhere. So let's make that, let's run it again so we can see threshold is 4, sum of weight is this, there's no gluten, we can go. So I want, oh no, I want a new line after there's, oh yeah. Let's get a new line, another new line there, so that makes our output a little bit cleaner. Yeah. And then we want to do something like that. Okay, so sum of values 0, 1, there's no gluten, we can't go. There's no gluten, we can go. That is a problem. That's a problem. Let's see why is that a problem? Because this should one. Okay, cool. So this one has gluten, we can't go. This one does not have gluten, we can go. Let's look at that. There's no gluten, we can go. There's no gluten, we can go. So there's a problem here. This shouldn't fire. This shouldn't fire. This shouldn't fire. So we said return over. I think we realized that it was under. Okay. Under or equal. We want to use under or equal. Under or equal. That fixes it. I know that will make the problem go away, but that it's slowly, the thing that is happening is it's showing me my intuition is broken somewhere. Because I keep doing it the wrong way. There's gluten, we can't go. There's no gluten, we can't go. So this is fixed. But somehow, every time I get to consider this, I get to this. Return. Let's look at this formula again. So I want to look at this formula again so that I can sort of understand it. The minus bias thing is confusing me. This. So if the dot product minus the threshold is less than or equal to 0, and in Sigmoid neurons 0 is 0.5. In Sigmoid neurons 0 is 0.5 because 0 here you see 0.5 is 0. It's in the middle of 1 and 0. So if it is less than, if the thing minus if the sum minus the bias is less than 0.5, we should return 0. So why isn't it working for more than 0.5? Because we're returning a boolean. Why is my intuition wrong? So why does over 4 point... So if I do over 4... I made a fire thing that should fire if it finds gluten. By the way I've chosen my biases, which is the threshold, by the way, it's not a new term I'm introducing. By the way I've chosen my biases, my weight, and my values, I have made a little detector that finds gluten. But I am using it as though whenever you're going to make these little neurons, you're going to make them the most sensitive to the things you're most sensitive about. Regardless of whether you're sensitive about that thing in a good way or a bad way, the most important thing is the most sensitive thing. So what I've made is a neuron that detects gluten. But I keep assuming that this neuron will give me the decision the way I'm used to. This is the abstractions that we need. We are not aware our brains are making. So your brain detects gluten and it decides you shall not go. But because we have to do everything step by step in code, we're not realizing that when we detect gluten, we don't want to go. And what we've made is a gluten detector. And that's why we keep making that assumption of 0.5, and we keep making it to above 0.5. So you just want to tell them, but it has actually found gluten, but that's not what you want. So you want to check whether it fires or not. And if it does fire, it means it found gluten, so it shouldn't go. So this was the usage leaking into the library. But yeah. Anyways, that has been quite a cool chill out. I am surprised that diff has taken us an hour to generate that diff. It's gonna be a super small diff. So let's see the diff. Get diff. I mean, most of the library has changed, so it's fine. We've now come up with sigmoid inputs rather than just neuron inputs. We have a sigmoid input and a perceptron input that brings floats and values, and I think I can make... Anyways, I'm not going to prettify it right now, but later I'll make it so that you can only do 0.2f. I think the best way of doing that, I think I can probably already do that, is whenever there's an f, I can do 0.2f. Just let me see if I can do this quickly. F 0.2. 0.2. Print floats. Why am I trying to remember this? Google is here for this. Print floats. Yeah, 0.6. Okay, it's in between there. So I can do 0.2, and yeah, I can do 0.2, and I can remove that. And then I can go, where else are we printing a float? Where else are we printing a float? Where else are we printing a float? So let's do 0.2, and then 0.2. And then here I want to do something like 1.89, so that it's something. And then I want to do like 0.98. Let's see what happens there. And then let's do that. Let's play around with those numbers like that. And then Q, so that this is code changing, so that let's do that. That's quite exciting. Let's link it. Let's run it. A out. Yeah, that looks much better for me. There's gluten can go, so cool. So, oh, look at this. Look at this. We have a sliding scale. I wonder if we do 0.30, 0.332. Let's do that. We have a sliding scale. Oh, wow. I did not realize that we just did that. No. No. So the weight of the gluten is a bit too important. Let's say there was this tiniest amount of gluten, 0.2, 0.02, okay? 0.02. Let's make a sliding scale. So let's see. It's quite heavy. The gluten is quite heavy, so maybe let's weigh the cheese more. Let's weigh the cheese like 4.0. Still quite heavy. Let's say there's more cheese. 2.9, 3.98. There's so much cheese. There's so much cheese, and then inside the cheese there's hidden gluten. Wow. We have to decrease the weight. We have to go like the weight. So now we have to go like, we don't really care that much. We can say 2.5. But then that's still gonna be... This is so cool because, yes, we've made a sliding scale. I know what we need to do. We have made a sliding scale. And I want to print out how close this thing is 2.5. Yeah. Regardless, I think we're sort of jumping into implementations, and that's a little difficult. So grab this code from GitHub, experiment with it as much as you want. Let's see what you can come up with. Let's see what answers you can come up with. This is so cool. I'll see you guys next time we do something with intelligence. This is cool. And yeah, watch out for the weekly, daily episodes on Embedded. Cheers. Thank you so much. Oh.